Well, yesterday we looked at the sine rule. Now let's have a look at the cosine rule. Let's prove that one. Drawing the perpendicular height, so we'll call that h, but just the right-hand side of that base I'm going to call x. So in the triangle on the right, I could use Pythagoras Theorem to say h squared is b squared minus x squared. Triangle on the left, I can say, well, c squared is h squared plus a minus x squared. Substitute in for h squared, and tidying that up, I get that c squared is b squared plus a squared minus 2ax. But if I have a look at that right-hand triangle there, x on b is the cosine of c. So x is b cos c. Sub in, and we get our cosine rule. Basically, it's Pythagoras' theorem, but we're taking into account it's not a right-angled triangle. See, if it was a right-angled triangle, I'd have the cosine of 90, which is, of course, 0, and we would get c squared is a squared plus b squared. So in any triangle, we could have for a squared, we could have it for b squared, we could have it for c squared, but notice the angle matches the side that you're trying to find. All right, let's do an example. We'll find t in this one. So t squared will be f squared plus m squared minus 2fm cosine of t. Now, look, in reality, I probably don't write that formula down each time, but it is important that you show the substitution step. So 3 squared plus 7 squared minus 2 times 3 times 7, cosine 98 13. From there, it's all calculator work, but don't forget to find the square root. Remember, it's t squared equals, so to find t, you need to find the square root of all that. So 8 units to the nearest whole number. Why did I do it to the nearest whole number? Well, because the question had their sides to the nearest whole number. So if they don't give me an idea of how to round off, I'll match what the question says. Let's do one where we find the angle. So f squared will equal a squared plus s squared minus 2as cos f. I can rearrange that formula and make cos f the subject. And in fact, a lot of people just remember the second formula. So cos f equals a squared plus s squared minus f squared over 2as. How do you remember it? Well, your Pythagoras theorem, but you take away the opposite side squared, and on the bottom, 2 times, and it's the 2 positive ones on top. So in this case, a and s. Substitute in, it's all calculator work from there. The nice thing about the cosine rule is it will pick up on obtuse angles. In this case, 140 degrees, 33. Hang on, this one, how am I going to do this? The angle that I know is not opposite the side I want to find. It's okay, you can still use the cosine rule for this. The angle I know is a, so I'll set it up so that it's a squared equals. So a squared is b squared plus c squared minus 2bc cos a. And I'll substitute in for that. The difference here is I actually know what a is, I don't know what b is. So I want to make b the subject. Well, I end up with a quadratic equation. B squared minus 14b cos 25 plus 40. So, quadratic formula, negative b plus or minus square root of, etc., etc., etc. So I get 2 possibilities. There are actually 2 triangles that I could construct with those dimensions. Now, unless they give me more information, I'm going to write both possibilities down. If they give me more information, then yes, I can possibly narrow it down to which one of the 2 answers that it is. Let's do an HSC one. So this one goes back to 2003. And we've got a typical sort of question. David's over here on a life raft, and Anna's in the cabin cruiser, and she's looking for David. But fortunately, they're in contact via a mobile phone. Now, David tells Anna, who's changed the way she spells her name, that he can see Mount Hope. And David's position from the mountain has a bearing of 109 degrees. Fortunately, David has a theodolite and can work out the bearing and the heights from everything there. The angle of elevation he can work out is 16 degrees. So lucky he knew that information. Anna, well, she can see Mount Hope as well. And she also has the equipment that can measure this. So she's worked out that it's a bearing of 139 and the angle of elevation is 23. But we also happen to know that Mount Hope is 1,500 metres above sea level. So how's Anna going to get there? She wants to know how far away is David and what bearing do we have to go and find David. So I'll just redraw the diagram there. Let's pull out some right angled triangles. So David's triangle, 16 degrees, and the height is 1500. There's Anna's triangle, 23 degrees. Let's draw the ocean. We'll place a compass at David. Now David knows the bearing of Mount Hope, so the base of the Mount Hope there is labelled B, is 109. Anna's somewhere else, and her bearing is 139. Now B is going to be the distance between, that green line there, and the bearing we want to find, we'll start at north, go around clockwise, that's what we want to find. So let's see if we can't find some more information here. Now using David's triangle, BD on 1500 will be the tan of 74. So BD, 1500, tan 74. Anna's triangle, she'd get that AB is 1500, tan 67. So let's place those two measurements on our triangle. Okay, we've got two sides and we want to find a third side. We need at least one angle in this triangle. What can we work out? Well, hang on, if I put a compass over there at the third vertex, we know all those norths are going to be parallel. So a bit of geometry, we can work out that NDB plus DBN double dash would be 180 co-interior angles. So DBN double dash is 71 degrees. I could do a similar sort of calculation to work out ABN double dash. It'll be 41 degrees. And ABD, well, that's the same as DBN double dash minus ABN double dash. So we get 30 degrees. We know the angle ABD is 30 degrees. So let's place that in. We now have a cosine rule situation. B squared is 1500 squared tan squared 67 plus 1500 squared tan squared 74 minus 2 times 1500 tan 67, 1500 tan 74, cos 30. Place that all in the calculator, and to the nearest metre we get 2,799 metres. So we know how far apart they are. Now for the bearing. How are we going to find that angle? Well, how about we find angle DAB first of all, because we know that the bearing from Anna to Mount Hope is 139. If we find angle DAB, add it to 139, and we've got the bearing that we're looking for. So all right, sine rule I'll use for this one. Now notice I've just put B there rather than the answer we found. I want to use the exact value. So I've got that stored in my calculator. So sine of DAB will be 1500 tan 74, sine 30, divided by that number I've got stored in my calculator. I get two possibilities though. It's either going to be 69 degrees 9 or 110.51. Now in this situation, it's important I know which one it is, because we want to sail on a bearing and go and rescue David. We don't want to get the wrong angle. So let's look at the situation. Let's assume the correct answer is 69 degrees 9. Now if that's true, then BDA must end up being 80 degrees 51. Angle sum of a triangle. But hang on, DAB has to be bigger than BDA. How do we know that? Because of the size of the opposite sides. That's telling us which angles are going to be bigger. Well, in that case, 69 degrees 9 can't be the right answer. So BDA must be 110.51. Bearing, add on that 139, and we get the bearing is 249.51. We now know what angle we have to go off to search for David, and we'll get there once we've travelled 2,799 metres. Okay, so 6J, 6K, well 6J is specifically on the cosine rule. 6K is then a mixture, and it will include some three-dimensional problems as well.